Everybody, welcome back to another business calculus video. In this video, we're going to be talking about marginal functions in economics. So, what is a marginal function? Why do we care about it? We've spent the past few videos developing the notion of a derivative and learning, okay, here's the practical how you take a derivative. What a marginal function is it's an economist's way of saying, okay, let's take this abstract concept and use it for something in the real world. So, formally, marginal analysis is the study of the rate of change of economic quantities. Alright, and anytime you see rate of change, you should instantly think derivative. So, derivatives are going to find their place in marginal analysis. So, what kind of economic quantities are we talking about? We're talking about things like cost, GDP, and more. Okay, so all very important things that we would like to know, not just, hey, what's the price of goods right now, but what's the price of goods becoming? Is it growing? Is it shrinking? Is my national GDP growing or shrinking? That's a pretty important thing to know, at least for those of us who actually care about the country's budget. So, not the politicians. Okay, we're going to start by talking about cost functions, which, exactly as the name implies, are functions that tell you how much something costs. So, one key thing that businesses might want to know is something known as marginal cost. And for those of you who haven't seen the term marginal cost in one of your other classes at this point, marginal cost is if a business is producing X units of some product, the marginal cost is the added amount to produce exactly one more unit. So let's say the total cost is given by a function c of x. Or really just a function capital C. Marginal cost is c of x plus 1 minus c of x. The cost of producing x plus 1 units minus the cost of producing x units is the cost of producing that final unit. Alright, so what does any of this have to do with derivatives? Good question. I'm going to try to work around the glare here. Even with all the blinds closed, somehow it all still seeps in. And yes, they are adjusted downwards already. Okay, so c of x plus 1 minus c of x is equal to that same thing divided by 1, right? Trivially. And this is really, really close. So about c of x plus h minus c of x divided by h when h is small. Okay, so that kind of makes sense, right? The difference between those two things, as long as we're picking a small enough h, maybe h is less than 1, right? As long as it's small enough, these two quantities are going to be relatively close to each other numerically. Okay, but this quantity, if we're working with small h, is going to be really, really close to the limit as h goes to 0 of c of x plus h minus c of x over h. Right, because that's what a limit is. It's what's happening to the function as variable gets close to something. So as h is getting close to 0, aka for small h, these two quantities are getting really, really close to each other. Namely, this quantity and the overall limit. But this is precisely the definition of c prime of x. And you might say, okay, cool, I get how we get that this is kind of close to that, but why wouldn't I just calculate this? This is just subtraction, and here I have to take a derivative. Good question. Here's the short answer to it, and then we'll get to the longer answer in a few chapters when we talk about differentials as to like why these abouts essentially make sense. But here, the short answer for now is maybe your cost function is really difficult to compute. Even for a computer, right? Different functions actually take different amounts of time for computers to know, and even complicated functions can take a long time for a computer, right? Now, a long time might be a few seconds. Okay, that's not that bad when you're only calculating it once, if you're only calculating one cost, but when you're working with millions or billions of cost calculations that you need to do every day, then that extra computing time really starts to add up. But the derivative is actually going to be simpler to compute most of the time than this up here. So it helps us to work with that. Derivatives are essentially known as the nearest linearization to the function. And linear things are easy to compute. So that's why, in short terms, we might want to work with c prime of x instead of c of x plus 1 minus c of x. Because computers. So, if we're going to be working with c prime of x, we should probably give it a name. Never mind, I already defined marginal cost, so I guess I don't need to write that down. But yeah, let c of x be a total cost function. So if we have some function telling us how much it costs to produce our product, c of x, then c prime of x is the marginal cost function. Please note, c prime of x does not measure the actual marginal cost, right? This would be the actual marginal cost, but it approximates it well. These are close to each other numerically. This is easier to compute for computers most of the time. So yeah, marginal cost function. In economics in general, the word marginal instantly means derivative of. So you have a cost function, the marginal cost function is going to be the derivative of that. You have a revenue function, the marginal revenue function is the derivative of that, and so on and so forth. Let's do an example. suppose a software firm is producing disks. Who uses disks anymore, right? This with their latest product. Pass my class 10. Supposedly pass my class 10 is different than pass my class 9, only in that they put a 10 at the end, but that's just a rumor. Okay, so to produce X units, per day, it costs them C of X equal to 0.1234 zeros 1 x cubed minus 0.004, sorry, 3 zeros, 0004 x squared plus 0.03 x plus 100. Our goal is to find the marginal cost function and evaluate it at x equals 100, 200, and 300. All right, so what are we doing here? What is this telling us? It's saying, hey, find the marginal cost function, and then we're going to find out how much would the cost of producing the 101st unit be, roughly. How much would the cost of producing the 201st and 301st units be, roughly? So let's actually do it. All right, so the marginal cost function, which I'll abbreviate as MCF, is just, by definition, the derivative of C of x. So we calculate C prime of x, which is what? Okay, d dx of C of x, which is, okay, by the sum rule, we split each of these things up. By the scalar multiple rule and by the power rule, we can compute the rest. So, try it yourself. You should get 0.12343 x squared minus 0.0008 x plus 0.003. Alright, so that's our marginal cost function. Done. And now we evaluate it, which means we need to find C prime of 100. Use a calculator for this. When I write stuff on the test, I will write it so a calculator will hopefully not be necessary. You'll still be allowed one, but you shouldn't need it. Okay, so C prime of 100, if you evaluate it, would give you 0.25. We need C prime of 200, right? That's what it means to evaluate at 200. And that would give us 1.07. And finally, we need C prime of 300. changed my number on here without even realizing it. Let's do 260 instead of 300. I think 300, when I was writing the example, 300 came out to be a bad number. So I changed it to 260. I changed it in the second part, not the first. So, whoops. That's what I get for writing lesson plans late at night. Okay, C prime of 260 in this case. So this would be the marginal cost of producing the 261st unit. And that would give us 1.85. All of this is in dollars, of course. So that kind of makes sense. It would cost me 25 more cents to produce the 101st unit from the 100th unit, $1.07 to produce the 201st unit, and $1.85 to produce the 261st unit. So you can measure that against your unit price and be like, well, is it really worth it for me to keep producing anymore? Am I going to be making a profit if I make more? All right. So that's a marginal cost function and tells you, okay, how much does the next one cost? But what if we wanted to find our marginal costs per capita? Or really just even our costs per capita? Well, to do that, all we need to do is take an average. Average of what? Average of all of our costs. So, definition for us. Same start. We'll let C of x be a total cost function. The average cost function which we will denote as C bar of x. So C of x, we put a little bar over the C, is, okay, so the formula for C bar of x will be C of x divided by x. So we ask ourselves, okay, why is that a valid formula? Well, what we're doing is we're taking the cost of producing x units and dividing it by x units. And that's telling us, okay, how much is each unit costing me on average, right? Because each unit might be costing you a different amount of stuff. For instance, the first unit might be costing you a lot more than the rest of them, since to produce the first unit, you need to get the factory up and running, right? So you have all those costs, and you don't incur those costs again on the second unit, right? But those costs start averaging out. So that's our average cost function, C of x divided by x. And of course, as soon as we have a function, we can talk about the marginal version. So C bar prime of x is the marginal average cost function. So what this function does is it answers the question of, on average, how much is my marginal cost? Okay, let's do an example. Let's say a goods cost function is C of x equal to 300 plus 40x. And let's find both of these things, the average cost function and the marginal average cost function. that's just a direct application of what the definition of these things is. C bar of x is just C of x divided by x, aka 300 divided by x plus 40. Nice and simple to compute. We can also rewrite that as 300 x to the negative first plus 40. The reason for doing that is to compute the marginal average cost function, because now we can just apply the power rule for that derivative. C bar prime of x should equal dx 300 x to the negative first plus 40, which is 300 ddx x to the negative first plus ddx 40, which is really trying to avoid that glare there. 300 times negative 1, so negative 300 x to the negative second. So we're going to have negative 300 divided by x squared, and then that's it. Because the derivative of 40, or any constant, is 0. Alright, so why do we care about these two things? What do those two results tell us other than the definition? Well, let's just make a couple quick observations about those functions that tell us useful information about this good. So, let's note that C bar of x, heck, I'll even use the formal notation since we're in calculus class. The limit as x goes to infinity of C bar of x is what? Well, okay, as x gets really, really big, this term gets really, really small, so we're just left with 40. Okay? So, what does that tell us? As we produce more and more, on average, each unit has cost 40. Okay, so that's a good thing to know. Because it says, hey, as long as you produce more and more, right, as the number of units you produce gets larger and larger, eventually your cost stabilizes. And that's a good thing, right? If that cost shoots up towards infinity, then maybe you need to find a more efficient way to produce your product, because it's going to be costing you more and more each unit you produce. Let's also notice that C bar prime of x is always less than 0. We have negative number divided by x squared is always positive. So this is always less than 0. What does that tell us? Okay, let's think about what it means for a derivative to be less than 0. We'll show this, or we won't show it, but we'll be given an explicit theorem about this in a couple chapters from now. But think, a derivative less than 0 means that the tangent line is going downwards, which intuitively means that the function is decreasing right there. So C bar of x is always decreasing. Your average costs are going down. And that's a key difference between your average cost function and your true cost function, right? Your true cost function is always going up, but this is saying on average, it'll be going down. Okay, so C bar of x is always decreasing, which means C bar of x is always going to be strictly greater than 40. If it is limiting to 40, that means it gets close to 40 as we go further. However, If it's always decreasing, that means it's always above 40 and going down towards 40. In short, I know that my cost function is going to be doing something, my average cost function is going to be doing something like that. And stabilizing out towards y equals 40. So that's useful information that you can just get without doing really any additional work. So that's why finding these things is useful. Even if you didn't want them for their own sake, it gives you some nice info about them. Yeah, well, this is already started. Okay, so that's cost function, measuring essentially the bad things that are happening to your business. Let's talk revenue functions. And revenue functions are essentially measuring not the money you make off each product, but the amount of money you bring in by selling the product, right? The amount of money you're actually making is your profit, and we'll get to that in a bit. But yeah, so if a company could always charge the same price for their good, so let's say they could always charge P dollars per unit of their product. Then the amount of money they generate, their revenue, would be given by the function r of x is equal to p times x. If I'm charging the same amount per good and I sell x goods, how much did I make? Well, I made the amount I sold times how much, or sorry. Yes, that was actually the correct language. I made the amount I sold times how much I make off each sale. Okay, well that's all well and good, but those of you who have taken economics courses know price is rarely a constant thing, right? It's always kind of fluctuating according to the laws of supply and demand. I guess I should say where x is. Alright, so if price is affected by laws of supply and demand, it's affected by the amount of stuff we've sold, because that's the amount of our products in the market. So often P depends on x. That is, P is equal to some function of x. Alright, so what does that tell us about revenue functions? R of x is going to be equal to still p times x, but p is now a function. So, rewriting it ever so slightly, it's x times some function of x. Alright, just like we defined marginal cost, let's define marginal revenue. The marginal revenue is the actual revenue gained from the sale, sorry, there's a lot of writing in this chapter, but so be it. From the sale of an additional unit of a commodity, given that sales are already at a certain level. So, in other words, r of x plus 1 minus r of x. And for the exact same reasons as our marginal cost function, it is well approximated by the marginal revenue function. Which we see marginal, we think derivative. So this is going to be r prime of x. Alright, so that's revenue. How would you compute r prime of x? Well, once you have your f of x, right, so once you know how your price relates to the amount of your product that you've sold, then you can take the derivative of this, apply the product rule, follows pretty naturally. Okay, that's all well and good, but what businesses care about the absolute most is their bottom line, their profit. So, if a commodity has cost function c of x and revenue function r of x, its profit function capital P of x is going to be given by revenue minus cost. So, in other words, P of x is R of x minus C of x. So finding marginal profit is the same as finding marginal revenue minus marginal cost. That is, by the sum rule, P prime of x is just R prime of x minus C prime of x. So by studying revenue and cost individually, we actually get information about the profit together. Okay. I suppose I should say that in some words. P prime of x is the marginal profit function. And exactly like the other two, it's going to approximate the amount of gain or loss that results from the sale of an additional unit of your product. All right, that's that page. That's done. So let's do some examples with these profit functions. Start kind of gluing all this stuff together. I miss the Cal Poly chalkboards, which are about 8 times larger than this. Okay, Suppose Sony is producing the new Annoy My Roommates speaker. Is free for those who never use it. So there you go, free product. But for everybody else, the price is modeled by f of x equal to negative 0.04 x plus 800. So that's negative 0.04 x plus 800, where x is the number of units sold. So that's our price, and let's say we also know how much it costs us to produce things, right? These are the things that a business will know off the top of their head. So the product has cost function capital C of x equal to 200x plus 400,000. So let's think about that. Right? When x is equal to 0, before they even produce anything, it costs them $400,000 to even have their plant up and running. And then it costs them $200 for every speaker they want to produce from there. Kind of an expensive product for them to produce. Really, no real world company would be that expensive. I just fudged numbers to make things nicer for us. But numbers is as numbers does, and as long as you know the concept, you can use it for any numbers. Okay, so let's say we want to find the profit function and the marginal profit function. So again, profit function, p of x, marginal profit function is the derivative of that p prime of x. So how do we find p of x? Well, we know p of x is revenue minus cost. I have a cost function, but I don't have a revenue function. Or do I? Revenue is x times f of x, where f of x is our price function. We have our price function right here. So we actually do have all we need. X times negative 0.04 x plus 800 minus 200x plus 400,000. Okay, and this is all just algebra. We do the subtraction out, we're left with negative 0.04 x squared plus 800x minus 200x, so plus 600x minus 400,000. So this is a deeply non-profitable product, until you produce enough that this linear term can start overwhelming all of that. But if you produce too much, then it will start costing you more again, because it's quadratic. All right, cool stuff. Now, to find the marginal profit function, we're going to find p prime of x. P prime of x is equal to negative 0.08 x plus 600. All right. There you go. There's p prime of x and p of x. Exactly what we set out to find. All right. So there's one more kind of area for this whole economic marginal analysis thing that is really important. Elasticity of demand. So what is elasticity of demand? Well, let's give a kind of informal definition of what we want from elasticity of demand, and then mathematically we'll see what it takes for that to occur. What we want is elasticity of demand to measure how a small percent change in price of some commodity affects the percent change in the demand for that quantity. So this is kind of how you start talking about your supply demand curves, right? How is your price actually affecting, well, demand in this case? Okay, well that's what we want elasticity of demand to measure. How do we actually get a formula for it using calculus? So, let's first make a definition. The relative rate of change of a differentiable function f at x per unit change in x is f prime of x divided by f of x. And rewriting this as a percent, this is just 100 f prime of x over f of x percent. Alright, so why does this definition make sense? Well, rate of change is derivative, so f prime of x. Here we're taking f prime of x divided by f of x, so that's expressing, hey, how is the derivative changing with regards to, well, I guess that's bad language here. What's the relative amount of change of the function with regards to where the function is at, right? Because this is how the function is changing, this is where the function is at. Okay, so we're going to define relative rate of change as f prime of x divided by f of x. Okay, let's make another definition. Or I guess not a definition, let's do some quote-unquote side work as we build up to our definition for elasticity of demand. widely agreed that demand is a function of price. Just like price is a function of demand. In fact, they depend on each other in the same way, right? If you have a function saying, oh, here's how demand is related to price, then the inverse function of that is how price is related to demand, and so on and so forth. Okay, so we can write x is equal to f of p. Careful, this is not the same f as in our f of x where we had p was equal to f of x. This is a different function f. We don't know either of them. We're using the same letter for both. Yes, that's bad notation, but it's also what your book uses, and I would rather not go against the book because that's going to confuse more people than me fixing the issue. If you want to put like a little g, so it was x equals g of p or something like that, I would recommend it. Okay, so where x is the quantity demanded of some commodity, and p is the price of the quantity. Okay, so applying this definition here, the relative rate of change of f with respect to p it's a lot of abbreviating right there, but relative rate of change of our function f with respect to the variable it depends on, p, is, by definition, f prime of p over f of p, aka 100 times f prime of p divided by f of p percent. And that percent is crucial, right? We can't just multiply by 100, but we have that percent there. Okay, well, why mention that? That's the relative rate of change, essentially, of demand with respect to price. But also, the relative rate of change of the price. So now we've talked about, okay, here's how the function is changing with respect to the price relatively, but how is the price relatively changing with respect to the price? Well, this, by our same thing, is price has function p, right? In terms of itself. So dvp of p divided by p. Again, applying our relative rate of change definition now to the function p. Okay? Well, derivative with respect to p of p is just 1 divided by p. And now we have all we need to define elasticity. I'll also write that as 100 divided by p percent to keep things consistent, and since we want to be working with percents earlier. So, the ratio percent rate of change of F divided by percent rate of change of P aka how demand is changing, percent change in demand divided by percent change in price, aka that elasticity that we wanted to measure, is equal to 100 F prime of P divided by F of P percent over 100 over P percent. Do all the arithmetic canceling out, and you get P times F prime of P divided by F of P. So this is very close to our definition of the elasticity of demand. We're going to put one extra term in there, and we'll see why. All right. So, definition. If F is a differentiable demand function, made it fit. So, differentiable demand function F then the elasticity of demand. So let's write x is equal to f of p. The elasticity of demand at price p is capital E of P equal to negative P times F prime of P divided by F of P. Okay, so if we have a demand function where X is demand and it's depending on the price, elasticity is negative, the quantity we found earlier. Okay, why the negative of it? Well, let's think about this. Demand and price are kind of inversely correlated, right? Demand drops when price increases, and demand increases when price decreases. That means F prime of P is, for almost all goods, going to be negative, right? So price is positive, demand is positive. That means this whole quantity would be negative, and economists just didn't want to work with a negative number for some reason. So they slapped a negative sign on the front and they said, this is our elasticity of demand. All right, so we have a couple of categories for elasticity of demand. Demand is elastic at a price P if E of P is greater than 1. It is unitary if E of P is equal to 1. And it is inelastic if E of P is less than 1. So let's think about those definitions, why they kind of are good words for that. We're saying, hey, if E of P is greater than 1, that means the rate of change is overpowering the actual change in the demand. Right, so it's changing more than the demand change. In other words, we're having a small change in price cause a greater change in demand. Unitary, if a small change in price causes roughly the same change in demand, and inelastic, if a small change in price causes even less of a change in demand. Basically, elastic goods, it's easier to kind of move along that demand curve. And you can see, I think it's page 208 of your book for a full discussion of this. Should be 208, assuming versions are the same and everything like that. Okay, let's do an example. Let's consider our previous example, the annoy my roommate speaker one. Where we had our demand function given by p is equal to negative 0.04x plus 800. Let's find E of p and compute E of 50. All right, so here's a function giving price in terms of demand, but to find E of p, I need demand in terms of price. So what we're going to do is we're going to solve for x in terms of p. So we have that going from here. P minus 800 is equal to negative 0.04x. Dividing both sides by 0.04 is the same as multiplying them by 25. So we're going to have negative 25p plus 800 times 25 is, let's see here, 8,000, 16,000 plus 4,000, 20,000. Is that the correct number? Zeros, 1, 2, 3, 4. Yes. Great. Okay. Yes, it is 20,000. Goodness gracious, I'm getting old. Okay, so we have negative 25p plus 20,000 is equal to x. All right, so where do we go from there? We need to find our elasticity, which means we need to compute this thing. Make sure to get written down if you don't have it already, because I'm about to erase it. So, by definition, E of p is equal to negative p times f prime of p over f of p, which in this case, right, we need dx dp. So this is f of p. And that tells us that f prime of p is just negative 25. Pretty nice and constant right there. So we have negative p times negative 25, divided by negative 25p plus 20,000. That'll be 25p divided by I'm just going to rearrange that as 20,000 minus 25b. Alright, so that is our elasticity function. And now to compute E of 50, we just plug 50 into this function here, which I'm going to use a calculator for because I did not write it down ahead of time. Alright, so according to my handy dandy little phone calculator, this is 0.06 repeating. Alright, so we have a very inelastic good here, at least at 50. Right? Once you are at a price of 50, then it becomes very hard for it to change from that point. Alright, that's our example, and that's the end of our video. See you guys in the next one.